Bonding the metal pole to both the equipment grounding conductor and the ground rod is proper and provides both lightning protection and a low impedance path for clearing ground faults. Connecting the pole to the equipment grounding conductor will not make the equipment grounding conductor path between the rod at the pole and the service a grounded electrode conductor instead of an equipment grounding conductor, as the equipment grounding conductor is still connected to the service panel and is not used to ground the electrical system. The National Electrical Code requires that lighting poles be grounded in accordance with Article 250.52 Grounding Electrode Conductor, or Article 250.56 Grounding Electrode System. Article 250.52 requires that the metal pole be connected to the grounding electrode system by means of a grounding electrode conductor. The grounding electrode conductor must be sized in accordance with Table 250.66. Article 250.56 requires that the metal pole be connected to the grounding electrode system by means of a grounding electrode conductor. The grounding electrode conductor must be sized in accordance with Table 250.66. Additionally, the metal pole may be bonded to the grounding electrode system by means of a bonding jumper. The bonding jumper must be sized in accordance with Table 250.102. In the specific case of using a ground rod as the grounding electrode system, connecting the metal pole to the ground rod using a grounding electrode conductor is necessary. The grounding electrode conductor must be sized in accordance with Table 250.66. Additionally, bonding the metal pole to the ground rod using a bonding jumper is a viable option. The bonding jumper must be sized in accordance with Table 250.102. By bonding the metal pole to both the equipment grounding conductor and the ground rod, a low impedance path is provided for clearing ground faults and lightning protection. Now let's delve deeper into understanding these concepts and code requirements. The equipment grounding conductor, often referred to as the EGC, plays a vital role in electrical safety. Its primary function is to provide a low impedance path back to the source, typically the service panel, in the event of a ground fault. This low impedance path facilitates the rapid tripping of the overcurrent protective device, such as a circuit breaker or fuse, thereby minimizing the risk of electrical shock or fire. In contrast, a ground rod, also known as a grounding electrode, serves a different purpose. It establishes a connection to the earth, providing a path for fault current to dissipate into the ground. While a ground rod can contribute to overall system grounding, it is not designed to be the primary path for clearing ground faults. Relying solely on a ground rod for fault clearing can result in a high impedance path, which may not allow the overcurrent protective device to trip quickly enough, leading to potential hazards. Therefore, the NEC emphasizes the importance of using an equipment grounding conductor in conjunction with a ground rod to ensure both effective fault clearing and lightning protection. Article 250 within the NEC provides comprehensive guidelines for grounding and bonding electrical systems. It outlines the requirements for grounding electrodes, grounding electrode conductors, equipment grounding conductors, and bonding jumpers. Understanding these requirements is crucial for ensuring the safety and reliability of electrical installations. Article 250.52 specifically addresses grounding electrodes, which are the means by which the electrical system is connected to the earth. Common types of grounding electrodes include ground rods, ground plates, and underground metallic water pipes. The NEC specifies the minimum size and installation requirements for each type of grounding electrode. Article 250.66 provides the sizing requirements for grounding electrode conductors, which connect the grounding electrode to the service equipment. The size of the grounding electrode conductor is determined based on the size of the service entrance conductors. Table 250.66 provides a convenient reference for determining the appropriate size of the grounding electrode conductor. Article 250.102 addresses bonding jumpers, which are used to connect different metallic parts of the electrical system together to ensure electrical continuity. Bonding jumpers are essential for minimizing voltage differences between different metallic parts, which can reduce the risk of electrical shock. Table 250.102 provides the sizing requirements for bonding jumpers based on the size of the circuit conductors. Now let's consider the specific case of grounding a lighting pole. As mentioned earlier, the NEC requires that lighting poles be grounded in accordance with Article 250. This typically involves connecting the metal pole to both the equipment grounding conductor and a grounding electrode, such as a ground rod. Connecting the pole to the equipment grounding conductor provides a low impedance path for clearing ground faults. This is typically achieved by running an equipment grounding conductor from the service panel to the lighting pole and bonding it to the metal structure. Connecting the pole to a grounding electrode provides a path for lightning energy to dissipate into the earth. This is typically achieved by driving a ground rod near the base of the pole and bonding it to the metal structure. It is important to note that the grounding electrode should be installed in accordance with the NEC requirements, including the minimum depth and spacing. When installing a ground rod, it is crucial to ensure that it is driven deep enough into the earth to make good contact with the soil. The NEC typically requires a minimum depth of 8 feet for ground rods. Additionally, if multiple ground rods are used, they should be spaced at least 6 feet apart to avoid reducing their effectiveness. The size of the grounding electrode conductor connecting the pole to the ground rod should be determined based on Table 250.66. The size of the bonding jumper connecting the pole to the equipment grounding conductor should be determined based on Table 250.102. In addition to the NEC requirements, local codes and regulations may also apply to the grounding of lighting poles. It is important to consult with a qualified electrical inspector or engineer to ensure that the installation complies with all applicable requirements. Proper grounding of lighting poles is essential for ensuring the safety of both people and equipment. By following the NEC requirements and best practices, you can minimize the risk of electrical shock, fire, and equipment damage. Remember that electrical work can be dangerous, and it is always best to consult with a qualified professional if you are not comfortable performing the work yourself. Furthermore, it's essential to understand the role of impedance in grounding systems. Impedance is the total opposition to current flow in an alternating current circuit, encompassing resistance and reactance. A low impedance path is crucial for effective fault clearing because it allows a large fault current to flow quickly, tripping the overcurrent protective device. In contrast, a high impedance path restricts current flow, potentially delaying the tripping of the protective device and increasing the risk of hazards. The equipment grounding conductor provides a low impedance path because it is typically made of copper or aluminum, which are excellent conductors of electricity. Additionally, the equipment grounding conductor is sized to carry the maximum fault current that the circuit is likely to experience. The ground rod, on the other hand, typically has a higher impedance than the equipment grounding conductor. This is because the earth is not as good a conductor of electricity as copper or aluminum. Additionally, the ground rod is not typically sized to carry large fault currents. Therefore, relying solely on a ground rod for fault clearing can result in a high impedance path and delayed tripping of the overcurrent protective device. To further enhance the effectiveness of the grounding system, consider using supplemental grounding electrodes in addition to the ground rod. Supplemental grounding electrodes can help to reduce the overall impedance of the grounding system and improve its ability to dissipate fault current. Common types of supplemental grounding electrodes include ground plates and underground metallic water pipes. When using supplemental grounding electrodes, it is important to ensure that they are properly bonded to the main grounding electrode and the equipment grounding conductor. Another important consideration is the condition of the soil surrounding the grounding electrode. The soil's resistivity can significantly impact the effectiveness of the grounding system. Soil resistivity is a measure of how well the soil conducts electricity. Low soil resistivity is desirable because it allows fault current to flow more easily into the earth. High soil resistivity can impede the flow of fault current and reduce the effectiveness of the grounding system. Factors that can affect soil resistivity include moisture content, temperature, and the presence of minerals and salts. In areas with high soil resistivity, it may be necessary to use special techniques to improve the grounding system's performance. These techniques may include using multiple ground rods, chemical ground rods, or ground enhancement materials. Chemical ground rods are filled with chemicals that help to reduce the soil resistivity around the rod. Ground enhancement materials are substances that are added to the soil to improve its conductivity. Regular inspection and maintenance of the grounding system are also essential. Grounding connections can corrode over time, which can increase the impedance of the grounding system and reduce its effectiveness. It is important to periodically inspect all grounding connections and tighten or replace them as needed. Additionally, the grounding electrode should be tested periodically to ensure that it is still making good contact with the earth. Ground testing can be performed using a ground resistance tester, which measures the resistance between the grounding electrode and a remote reference point. A high resistance reading indicates that the grounding electrode is not making good contact with the earth and may need to be replaced. In summary, proper grounding of lighting poles involves connecting the metal pole to both the equipment grounding conductor and a grounding electrode, such as a ground rod. The equipment grounding conductor provides a low impedance path for clearing ground faults, while the ground rod provides a path for lightning energy to dissipate into the earth. It is important to follow the NEC requirements and best practices for grounding and bonding to ensure the safety and reliability of the electrical installation. Additionally, consider using supplemental grounding electrodes, improving soil conductivity, and performing regular inspection and maintenance to enhance the effectiveness of the grounding system. Remember to consult with a qualified electrical professional for any electrical work or if you have any questions about grounding and bonding. They can provide expert guidance and ensure that the installation complies with all applicable codes and regulations. The grounding electrode conductor, as mandated by the NEC, connects the grounding electrode to the electrical system's grounded conductor, the equipment grounding conductor, or both, at the service equipment or at the source of a separately derived system. Its primary purpose is to provide a low impedance path for fault current to return to the source, facilitating the rapid operation of overcurrent protective devices like circuit breakers or fuses, thereby minimizing the risk of electrical shock and fire hazards. Proper sizing of the grounding electrode conductor is crucial for ensuring its effectiveness. The NEC specifies the minimum size requirements for grounding electrode conductors based on the size of the service entrance conductors or the derived system conductors. Table 250.66 in the NEC provides a comprehensive guide for determining the appropriate size of the grounding electrode conductor based on these factors. When selecting the grounding electrode conductor, it's important to consider the material used. Copper and aluminum are the most common materials, each with its own advantages and disadvantages. Copper offers excellent conductivity and corrosion resistance but tends to be more expensive. Aluminum is lighter and less costly but requires careful installation to prevent corrosion and maintain conductivity. Furthermore, the grounding electrode conductor must be protected from physical damage to ensure its long-term reliability. This can be achieved by routing the conductor through conduit or other protective enclosures. The installation should also comply with all applicable NEC requirements and local codes. In addition to its role in fault current protection, the grounding electrode conductor also plays a vital role in lightning protection. By providing a direct path to ground, it helps to dissipate lightning energy, reducing the risk of damage to electrical equipment and the building structure. This is particularly important in areas prone to frequent lightning strikes. Therefore, a well-designed and properly installed grounding system, including the grounding electrode conductor, is essential for ensuring electrical safety and protecting against both fault currents and lightning strikes. Consulting with a qualified electrical professional is always recommended to ensure that the grounding system meets all applicable codes and provides adequate protection for the specific application. The bonding jumper, a critical component in electrical systems, serves to ensure electrical continuity and conductivity between metallic parts that are likely to become energized. Its primary function is to create a low impedance path for fault current, enabling the rapid operation of overcurrent protective devices and minimizing the risk of electrical shock. Bonding jumpers are commonly used to connect metal enclosures, raceways, equipment frames, and other non-current carrying metal parts of the electrical system. By bonding these parts together, any fault current that may flow through them will have a clear path back to the source, tripping the circuit breaker or fuse and energizing the circuit. The NEC provides specific requirements for the size and installation of bonding jumpers to ensure their effectiveness. Table 250.102 in the NEC outlines the minimum size requirements for bonding jumpers based on the size of the circuit conductors. Proper sizing is crucial for ensuring that the bonding jumper can safely carry the maximum fault current that may occur in the system. In addition to size, the material and installation of bonding jumpers are also important considerations. Bonding jumpers are typically made of copper or aluminum and must be installed in a manner that provides a reliable electrical connection. This may involve using appropriate connectors, tightening screws and bolts, and protecting the jumper from corrosion and physical damage. There are several types of bonding jumpers used in electrical systems, each designed for specific applications. Equipment bonding jumpers are used to connect equipment enclosures to the grounding system. Main bonding jumpers are used to connect the grounded conductor to the equipment grounding conductor at the service entrance. System bonding jumpers are used in separately derived systems, such as generators and transformers, to establish a grounding connection. Proper installation of bonding jumpers is essential for electrical safety. Incorrectly installed well-sized bonding jumpers can compromise the integrity of the grounding system and increase the risk of electrical shock. Therefore, it is important to follow the NEC requirements and consult with a qualified electrical professional when installing or modifying bonding jumpers. Regular inspection and maintenance of bonding jumpers are also recommended to ensure that they remain in good condition and provide reliable electrical connections. This may involve checking for corrosion, loose connections, and physical damage. Any damaged or corroded bonding jumpers should be replaced immediately to maintain the integrity of the grounding system. In summary, bonding jumpers play a vital role in electrical safety by providing a low impedance path for fault current and ensuring electrical continuity between metallic parts. Proper sizing, material selection, installation, and maintenance are crucial for ensuring the effectiveness of bonding jumpers and minimizing the risk of electrical shock. The information provided serves as a general overview and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician for specific guidance on electrical installations and safety practices.